we're going to look at inverse functions. So part of inverse functions is the notation to start with. So f of x represents some function, and then its inverse looks like it's putting the function to the power of negative 1. What they want to make sure that you're aware of is it's commonly seen that if you have, for instance, a number. Let's say you had the number 5 to the power of negative 1. That would be the equivalent of its reciprocal, 1 over 5. This notation, the inverse of the function is not equal to the reciprocal of the function. So they want you to be aware of that the notation is different. Okay, so that's a big first part. It's not just the reciprocal. An inverse function has a whole different algebraic way of solving what it's equal to. So in math, we use a lot of different mediums to represent stuff. We use our algebra. So for instance, if we have some function f at x is equal to, I'll write it in, write a vertex form of a quadratic here for us. So we have 3x minus 2 squared plus 3. This is your algebraic representation, okay? So here's our algebra. Then you also have a graphical representation, which will look something like this. Move this down. Let's do black. So we're going to just do a rough sketch of this one. It's got vertex at positive 2, so about 2, and positive 3. And it opens upwards. I'm going to change it to make it open downwards, and it's going to look something like that. It's going to look like it's vertically stretched, okay? Yeah. Okay, so there's our graphical representation of it. And then they'll also use tables are really common as a way of representing things, that could be very, very helpful. So in this case, this one's a little trickier. I'd have to memorize it. Let me just pull some numbers out. I know at least one of them. If this is my x value, then my f at x value, or the y coordinate, for instance, happens to be this one at positive 2, happens to be positive 3. And then if I had 1, negative 1, 3 would be 0, I believe, which means 3 would be 0. Okay, so we have sets of coordinates here, and this is your table. I'm going to close that door. All right. So those 3 representations, which are good ways for just understanding any function, they want you to be able to take it from any of these. So in other words, if you're looking at the algebra, you're looking at a graph, or you're looking at a table, can you find the inverse of the function? Yeah. So we'll look at this one specifically, and we'll start with its table. Okay. I could make a better table if I use Desmos with this one. Let me see if I got Desmos very quickly up here. Let's bring the Desmos. There we go. So we have f at x, we said, was equal to negative 3x minus 2 squared plus 3. Is that right? Yeah, there it is. What's nice about this program is it builds me a table really quickly. All right, so I did get my values right. 3 is 0. Awesome. Okay. So we have this table here. What I'm going to do is I'm going to steal those values and write them down because they'll be very, very helpful. So 0 was negative 9 and negative 1. None of that was recording there. Shoot.
No, it's all right.
It's okay. What we're going to do is we're going to take the algebra. So our algebraic representation, which is f at x, was equal to, and let's take a look at what it said here. Negative 3 x minus 2 squared plus 3. Okay? What we're going to do from here, if you're finding an inverse function, so if you're trying to find the inverse of that, you're actually going to take these 2 coordinates and you're going to swap them. Sorry, these 2 values, I should say, the variables. You're going to swap those 2 variables. Now, it's very common to change them to y and x for a student, just because this notation is a little tricky. Essentially, this notation's got 1, 2, 3, 4 different symbols to it, so students sometimes get confused, but you really do think of it as a variable in itself. So if it is easier for you, you can write it like this. Y is equal to negative 3. We still have the x. Everything else stays the same. And what we do is we just swap positions of x and y. So when we do that, we end up with x is equal to negative 3 y negative 2 squared plus 3. Okay?
Yeah.
Let me just fix that negative. Okay. Then what your goal will be is the same as before, is to isolate for y. So we got to start moving things to the other side. So we do, when you're isolating for variables, sometimes it's commonly known as reverse BEDMAS. You do your addition and subtraction first. So I have a plus here, plus 3. I'm going to move it to the other side, so we'll end up with x minus 3. That becomes our next movement. Is equal to negative 3 y minus 2 squared. Okay. Then I have this negative 3 here. So my division and multiplication, I'm going to divide both sides by that. Okay. On this side it cancels out. On this side it stays. So we now have x minus 3 over negative 3 is equal to y minus 2 squared. From here, well, to get rid of a power of 2, I need the opposite root. So I square root this. When I square root both sides, these operators, they cancel each other out. But on this side, we still have a square root. We've got y minus 2 on the right side, and then on our left side, I still have a square root of a fraction here, which may look confusing. I'm going to isolate it so it looks a little better for transformations. And then finally, the very last thing, we got to bring that negative 2 over again. So we'll end up with y is equal to the square root of, it's a terrible square root, negative 3. And then this is outside of the root, plus 2. Okay? So this is actually our new function. So what we have to remember to do is substitute back in at the very end the inverse function, because we've now found the inverse. Okay, once we've swapped them, we found the inverse of this. So the inverse is equal to, we'll try to make this a little cleaner, square root here. This 1 over 3, or this negative 3, I can kind of write it like this. Oops. So it looks a little more like graphing notation or transformations. We'll write it like that. And then this is outside of it, plus 2. So what we have now, this is some root function. And if I go back up to my graphical representation, oh yeah, that makes sense. When we flip a parabola on a 45, we get a root. Okay? And it happens to be going the other way, and it's been compressed. So if we go and take a look at it, we can actually figure this out by looking at this. Oh, this has a horizontal stretch by 3. It's been flipped on the y-axis because it's negative. Its coordinate starts at positive 3, or it's not quite a vertex when we have a root function, but if you were to call it a flipped vertex, it'd be at 3 and positive 2. When we go to look at that, all those things are true on our graph. 3 and 2 is here. This has a horizontal stretch by a factor of 3, and it's been flipped. Normally our root functions are going this way. This one's been flipped on the y-axis and goes back that way. Okay, so I tried to make sense of the information I got, but I don't technically have to if I've already graphed all of that. This is the algebraic representation of what we did. So what was really important here is figuring out that there's a couple of different ways we deal with inverse functions. If you have a table, you set up a table with your inverse here, and you just swap x and y values. Okay? If you have your graph, which we kind of missed this part in the video, but if we have our graph here, you flip it on a 45-degree angle. Okay, so it's been flipped on that. Now, trickier, it's easier said than done. Building a table first really helps with that because it just sets a bunch of coordinates and we just plot and then fit a curved line to it. Algebraically is the tricky part. We set it up. Sometimes it's easier to call this a single variable rather than f at x, which is still a single variable. We just have lots of symbols representing it. We swap the positions and then we isolate for y. And then in the end, we just swap back to the inverse. I can, and I'll do it here just so you can see. We can do it using the proper notation. It's just I know some students get a little confused. So when we flip this, so it's going to be the exact same process here, so I'll go through it quickly, but this part I'm going to talk a little more about. When we change the f at x and the x, this is when we're finding the inverse. So the x then comes over and replaces our f at x. But when we move the f at x over, we're going to write it as the inverse now. What we're saying is we're now solving for the inverse. And all we did was replace x with that value. We still have the negative 2 squared plus 3. But think of this as a single variable. Even though there's all kinds of notation around it, it's almost like its own little unit or a box, and you have to move it as one. You can't split this thing apart. Okay? So now, same process as before. I bring over 3. We get x minus 3 becomes negative 3. The inverse function minus 2 squared. Okay? We bring over or negative 3 here. That becomes the inverse function minus 2 squared. Okay, these two essentially canceled out. I'm going to make this look a little more like this so it's easier to see for our transformation. We're going to take the roots of both sides so that these two operators cancel out. That leaves us with our inverse function minus 2. We do have a square root over here now. Square root will read a negative third times x minus 3. And then the very last thing will be to move over that negative 2. So we'll end up with just the inverse function isolated. And then over here on our right side, we got our square root. So we know it's a root function, which is underneath the root. We still have these values. And we just moved over that negative 2, which we had done before, and it just becomes positive 2. So now we have the inverse function is equal to this algebraically. I know most students find it easier just to turn it into y and then at the very end just switch it, okay? Whatever works best for you is completely fine. But that is kind of like an overview of the 3 different ways you'll deal with inverse functions.